What is normalized data? Now, so far, we've talked about how the need to store various types of data leads to multiple tables, and we've seen one-to-many relationships between data. For example, one author can write many books. But we also saw how a one-to-many relationship between two entities becomes a many-to-many relationship. For example, a book can have multiple authors, and an author can have multiple books. With single-valued rows of data in tables and single-valued elements in each column, the need to use one-to-many relationships becomes our solution for these more complex relationships. But there's a more subtle thing that arises when we work with data in this manner: data normalization. Data normalization is when we find the most efficient means of storing the underlying semantic knowledge. If all we had was a single table with infinite rows and columns, we could model our library system kind of like this: title, author, Frank Herbert, Dune. Frank Herbert, Dune Messiah. Mark Polak, Spring Data. Oliver Dropbaum, Spring Data. Thomas Reisberg, Spring Data. Well, that's pretty straightforward in capturing all the information at hand. We have every book's title, and we have every author's name. And we can also see how each author is related to each book. But do you notice anything wrong, or at least anything that's not preferable? There's a lot of duplication. We can see Frank Herbert listed twice. The Spring Data book, while each author is only listed once, is itself shown 3 times. There's a lot of duplicate content when we put all the data into one big table. At a glance, it may not seem hard to find a given book. Just write something like this: select star from big table where title equals Dune. That would give us back a result set with 2 columns, Frank Herbert and Dune. And that looks all right, right? But what happens if we alter the parameter to Spring Data but change nothing else? Select star from big table where title equals Spring Data. This would give us a multi-line output: Mark Polak, Spring Data. Oliver Dropbaum, Spring Data. Thomas Reisberg, Spring Data. Well, now what? Is this right? Is it wrong? Well, the correct answer is it depends. This is an ambiguous result set because the table in and of itself doesn't tell us if it's a book table or an author table. How should we map this into our object structure that's in our application? One book with an embedded list of 3 authors? 3 author entries, each with a copy of the book entry? The database itself doesn't know nor tell us because this table is literally an entire database stored in one table. Since we requested select star, we're literally asking for everything the database has to offer. What we make of it is our problem. So let's refine the request a bit. What if we ask, who wrote Dune? Select author name from big table where title equals Dune. Results, Frank Herbert. That's straightforward. Who wrote Spring Data? Select author name from big table where title equals Spring Data. That output would show us 3 results: Mark Polak, Oliver Dropbaum, and Thomas Reisberg. Well, still looking all right. How far can we go with this? What books did Isaac Asimov write? Select star from big table where author name equals Isaac Asimov. The foundation, second foundation, that's 3 for 3. Is this the part where I mentioned that Isaac Asimov wrote like over 500 books in his career? Let's cut to the chase. Is there a limit on how far querying one big table is versus a database where the tables are split up into book, author, and book author like we had before? The answer is an emphatic no. There is no limit to querying such a table. You see, this big table is fundamentally what you get when you join together book, author, and book author based upon their relationships to each other. The intermediate result set from which the query filter is applied is the same thing. So what's the deal? Why go to all this trouble to split things up when we could just do this? Remember the duplication issue. We briefly mentioned it, but didn't delve too deeply into it. Maybe this is time to bring up the little fact. Isaac Asimov wrote over 500 books. He was one of the most prolific authors of the 20th century. We only have 2 rows represented here, but take what you see and multiply it by 250. Imagine storing the textual value of Isaac Asimov 500 times in a database. That string is 12 characters long, counting the space in the middle. It would take 6,000 bytes to store a 12-byte string that many times. Now, of course, disk storage is one of the lowest cost commodities in modern computing, so it can't purely be a disk consumption issue that's at stake, and it's not. What if you needed to update that value in the database? Isaac Asimov passed away in 1992, but imagine a modern-day author that was loaded into our library. What if our database tracked the date of their birth and their death, and we needed to make an update? Imagine updating 500 plus records to ensure they're all correct. Not only is that expensive, but there's an inherent risk of not completing the operation. How would we compensate for an update that only updated 499 out of the 500 entries? The next query for that particular author might return the wrong answer. This leads us to wanting to store every piece of information in a database once, and only once. The names Isaac Asimov, Frank Herbert, Greg L. Turnquist, Mark Polak, Oliver Dropbaum, and Thomas Reesberg should be stored once and only once in our database. And that way, any update only has to be once. And here we see the ultimate engineering trade-off. We can either speed up queries by having everything joined in one big table, or we can reduce duplication and risk of consistency and have everything stored once. To zoom out a bit, remember our 10 million row book and 5 million row author database representing our library? Imagine merging those tables into one big table. At a minimum, the thing would be at least 10 million rows, one for each title. It will certainly be more than that due to multiple authors. And more importantly, that big database would have many more columns, basically the number of columns of the book table plus the number of columns of the author table. When you structure your data such that you have no duplicate content, occupying the minimum amount of space possible, and only using foreign keys to link tables together, this is known as third normal form, sometimes depicted as 3NF. This is what the industry calls normalized data. With normalized data, you've taken the time to identify the exact relationship between the various entities. This relationship between various entities can be a complex process. There are times when you may map things one-to-one and later discover the need to change that relationship to one-to-many. Another relationship may be seen as one-to-many but later evolve to many-to-many. We've already seen that different relationships beg for different types of joins. Simply moving from one-to-many to many-to-many requires bringing in an intermediate table. Well, this isn't hard, but it isn't trivial either. And the joins needed to navigate through these relationships change. Perhaps you're thinking, why not just make everything many-to-many and go from there? While noble, that would require putting an intermediate table between every single entity table in the schema. We've already seen how we had to move from select book.title, author.name from book join author on book.authorfk equals author.id. We had to change that to select book.title, author.name from book join book author on book.id equals bookauthor.bookfk, join author on author.id equal book author to authorfk. And even further on to using left outer joins to ensure that we're bringing in books that have no author. Making everything many-to-many and optional dials up the verbosity and complexity of the whole structure. It's also important to recognize that the more tables you have, the more costly the storage. It also increases the maintenance and performance costs of proper indexes. Instead, it's best to capture the true relationship of your data to the best of your ability, and then let your data grow naturally over time. Which leads to another question. What happens when data grows and grows and grows?